title is Inference from Markov Chains. I mean, the techniques are more general than that, but we'll stick to the concepts are more general than that. But the main message of the first two sections is we have observations, we want to create a model. And so, you know, if these were, so y is going to always refer to a string of variables. We're going to have this time all the time in these problems. And if you were given something like this, you know, you might just go through and just fill it in. You know, cubic splines. You know, I guess a lot of you have seen that's a bad thing to do often. I mean, because you can basically, I made this look really good, but you can end up with, instead of, see this overshoot here, it can really get bad, you know. It's just, you know, and that's called overfitting, by the way. You know, the reason, I mean, the reason you don't necessarily want to exactly match your observations with your model is that trying to force a model to fit exactly causes it to explode elsewhere, which is the overfitting. That's just one example. But so this is a part of the course I really love because you have so many tools to cook up these models and then try to identify them. And Markov chains are a really nice example. You know, we like Markov models because we have tools for filtering, as we saw in the last week. I know I'm choking. And we also have techniques for system identification. So basically, we'd love to. This is dumb. But basically we could take the same data that you just saw here, the scalar data. It might the general setting that we're going to focus on is maximum likelihood estimation. This is the focus. This is not the only way to do this, but it's just we need to focus in on something. It's a very general technique. And so we have a parameter theta. We have a parameter which determines the model, and right here, A, B is theta. And in fact, we will apply what I talk about today to that exact problem. And we will come up with really sweet algorithms to estimate, you know, your transition matrix and your observation matrix based on observations, which is really wild. Like I said, probabilists are brave, and statisticians are brave. It's remarkable that you can you can do this, as we'll see. That you could just take a bunch of symbols, maybe like this wheel, like I've shown you, and then construct a Markov model that's consistent with those observations. And it's not going to cross through these points like this. It's a stochastic process. So, just in a statistical sense, we'll get the best fit we can. Okay, so there's so many things I want to say. So, anyway, let's define it. Okay, so I think it's really great that Bruce Hayek in the book uses an F for density and a P for probability mass function, but it's really cumbersome and it doesn't matter, okay? So I'm going to use P in either case, for either a discrete probability mass function or for a density, as I have been through the whole course, actually. So that's our model, and there's something called, so basically, given observations, so y here is a variable, right? We have a density. This is the density of y, or the probability mass function of y. So little y can take on any value. But we observe something from reality. We observed it's a beautiful day, even though they said it was supposed to be horrible. We stick that in, and we get an estimate of theta. Which is the most likely theta. And there it is. So just burn that into your memory bank. That's flashcard number 54 for this gentleman here. And the ML estimator, that's it, the most likely parameter. And note this is not Bayesian. Okay, so there's no prior associated with theta or anything like that. All right. Now, there is Bayesian statistics as well. So basically, you have the joint distribution actually, I should put in both. Basically, so we're in a Bayesian setting. Theta is considered to be a random variable, and we're given a prior. All right, and this is a model, and there's other estimators, all sorts of things you can come up with. Once you have if you put a prior on theta and assume it's a random variable, there's a million different kind of criteria for good, invariance of this. I don't want to get into it. I just think that we should just focus on ML, and if you want to learn about others, you can. All right, just know that in a Bayesian setting, there's a million other things you can do. All right. So let's let's see. Let's go through some examples. All right, so let's return to, obviously binary hypothesis testing exactly this. We have our observations are anything. I focused on discrete observations when I presented the material, but it doesn't really matter. Theta lives in it's just two values. So I'm returning to the binary hypothesis testing problems. I look at a sequence of observations, and basically Y is IID, but with marginal denoted mu theta, right? And so in the notation previously, I want to make sure my ones and zeros are the same. I'm going to say mu1 is equal to what we called Q, and mu0 is what we called P. So go back to your notes. Remember our notes over here? Here we have remember all that business. All right. Okay. So let's play around with this. So we only have two possibilities for this ML estimator. So we're just maximizing over theta equals 0, 1. All right. And so we're going to have theta hat of y is equal to 1. If and only if the likelihood ratio is greater or equal to 1. So L of y is just going to be equal to the ratio of these probabilities. Right. So saying that that theta equals 1 is a maximizer, since we only have two possibilities, we're maximizing over theta equals 1 or 0. I just look at the ratio, and if this is bigger than 1, I say that hypothesis 1 is true, theta equals theta 1, and if it's less than 1, then this is bigger, so I say that that 0 is true. All right. So that's the same as saying that that L is greater or equal to 0. So saying that little L of y is greater or equal to 1 is the same as saying that its log is greater or equal to 0. And I can divide both sides by t. As you'll see, that's a good idea, because what's the log of the likelihood ratio? It's I've got this is a product with 1s, and this is a product with 0s. So I get a product of the likelihood ratios. Oh, I see. That should be, oh my God, that's the big likelihood ratio. Max is born. I should not be so flustered. Yes, my grandson was born at 10 p.m. on Friday. Everything went well. Sorry, so this is a likelihood ratio for the string of length t, and because we're assuming it's IID, it's a product of these little likelihood ratios that were the subject of the course way back in the beginning of March or something, or February. All right? It's IID. That's why we have a product up here. All right? And now I'm looking at a ratio of these two guys, which are each products. They're all basically products of these ratios. Okay? All right, and so that's why I get this, and that's why I get this is equal to 1 over t times the summation k equals 1 to t of L of yk. Right, and we have a name for that, right? Did I have a subscript or a superscript? I don't know. Okay, so this statistic that we're looking at, that we say that hypothesis 1 is true if and only if this statistic is greater or equal to 0, is precisely the statistic that was the focus of the course. And so basically we're looking at this threshold rule where c equals 0. Okay, so c equals 0 never came up, I don't think, when we talked about this. You know, all we knew is that over and over again, like in homework and exams, I ask you to tell me what c is when you hit q, and what c is when you hit p. And here it turned out to be relative entropy, so it was positive. Here it was negative relative entropy, so it was negative. And there's a sweet spot in the middle where you get 0, and it turns out to be equivalent to the maximum likelihood test. All right? All right. So you're all much faster than me. Somebody else should take over. Anybody want to take over? No. Okay. All right. So we've done ML estimation before, or generalization. So more examples. So there's an example of 5.12 from the book. So this is a single observation, pretty boring example. Where I know that I'm assuming y is Gaussian with unknown mean that I'm calling theta, but the variance is known. Anything else would be really hard, you know. So basically, this is just set up to be easy. And so then you write down what do we mean then? We've got this py of y given theta, which is now a density. And that's just, you know, this is the density for Gaussian random variable with variance sigma squared and mean theta, because theta is the determines our model. Right? And you can imagine, I took a log here so I could get a sum and get something pretty here. I'm going to take a log here because it's an exponential. And this happens all the time. And so you take the log, and what do we have here? I've got a constant here which I don't care about. It doesn't depend on theta. Take it aside. And then I have a negative quadratic, so it's a concave function. We're trying to maximize over theta. I just want to get in your brains that we've got an optimization problem over theta. All right? And it's just a quadratic, so this basically right there, the maximizer is theta hat ml. And how do you find a maximizer of a nice smooth function? You take the derivative set equal to 0. And so when you do that, what do you get? Well, that disappears. You get y minus theta equals 0. So y equals theta hat ml of y is just equal to y. So that's
you
it.
get the same thing as like using the Bayesian as the non-deterministic in this case?
No. I haven't. No. I mean, if the question was, is if you have a Bayesian setting, do things change? Sure. Theta could be discrete.
What do I mean, like for this particular?
Nope. Theta could be discrete. So, for example, in a Bayesian setting, the prior could just be supported on 2 points. So it could be exactly like this. It could be that basically you have two possible means, mean 0, mean 1, for example. Yeah. So yeah, the Bayesian setting changes everything. Yeah, but you see, I mean, basically, you're taking that single observation and you're saying that's the mean. It's pretty, and that's the thing. I mean, you're always going to get really naive estimates with one observation. I mean, and you're just saying my one observation, because remember, theta is the mean. Theta is the mean for the model, and we just take an observation and say that's it. All right. Now you can see if my unknown was sigma squared, it would be a little harder because I'd have this log here and this, but you could still solve it. You know, so you could actually solve it with, if your model with both of these were unknown, you could still do it. Come with the most likely variance as well. All right. Another example. So take a Poisson random variable. This is just to get us in the mood. What does that mean? So I have to look this up again. It's 1 over... All right. Okay, so here we had a nice density, and now we have a discrete random variable. It doesn't make any difference. It's just the fact that we have a family of models parameterized by theta, and given an observation y equals y, so we saw an observation from nature, we want to compute theta hat m. All right, so nothing changes. I always have the same definition for the ML estimator. And what will I do? So now k is y. And you see it's very similar to this, right? I've got an annoying theta to the k. And I've got this e to the minus theta. And you know that taking logs will just kill it. So what's the answer? half of you must have worked it out already, right? I don't know. I don't know. Without doing any work yet, let me remind you that the mean is identically equal to theta. So just like here, the mean was theta, for a Poisson random variable, the mean is theta as well. You know, and so it turns out it's boring again. But let's do the. So again, we'll take logs, and I've got a, 3 terms I have to worry about. Oops. I got it? So I've done just 2 things. I've replaced k by y, and I've taken logarithms. All right? And this is what I hoped that some of you had done before I was finished. But all right, and so the same thing, I'm going to take the derivative with respect to theta and set it equal to 0. Because this, again, is a really nice concave function. I mean, take a look at it. This is a constant, it doesn't depend on theta, so you don't have to worry about it. The logarithm is a concave function, and I'm subtracting off a linear term. So the logarithm on its own would just be going off like that, right? But then I've got this linear term which crushes it downwards. So if you actually plotted this, and again, when theta goes to 0, this goes to minus infinity. So So I really encourage you to plot these things when you're doing it, just so you can center yourself, know what you're actually doing. So again, the maximizer here is what we want, so we take the derivative and set it equal to 0. All right? And what's the answer? So the derivative here is y over theta. And the derivative here is 1. And so just like Daniel predicted, the ML estimator is y. All right, one more example, because I want one more example that's not so trivial. A binomial. It's a good example, too, because it shows you have to be a bit careful. So now I'm going back to a situation like I have over here. We've got a string of a sequence like this. I'm keeping it capital, it's a random variable. Little y means it's observed, so I just think of it as a number and store it in a computer. And what do I mean by binomial distribution? So I've got, Actually, this one's actually, no, this one's not naive as well. There's one more, there's a fourth example, there's one last example after this that's less naive. All right, so basically I've got, the z's are really what capture the unknown information, because each one of them is just Bernoulli with parameter theta. Theta is between 0 and 1. So theta is the probability of success. You know, so Bernoulli means it's 0 or 1, and the probability of 1 is theta. And so we basically have sums of these, and we have the whole thing. And what is the ML estimator? Anybody have a guess of what the ML estimator will be? What would you do? Well, so before we do anything, what would you do if you were given this problem? So let's see, I sum up the y's. And you say average, and what does that mean? So the y's are already a sum of n terms. They're all independent. And there's t times n z's then, right? So when you say an average, you would divide by nt. Yeah, and it's got to be that. So I take it back. This one is also naive. This turns out to be correct. And let's just quickly go through it. Because it's cute the way it pops out. So you've got to go through and work out this monster. So now we have a string of y's, and at least they're independent.
How do you think he felt in the 17th century?
Yeah, I know. Yeah, they were much braver then. I'm not as brave. Okay, so at least they're all, the y's are IID, so we just have to work out these guys, and then you have a rule for the binomial distribution. And it is. So I've gotten yk successes, so it's theta to the yk, and I have and the probability of failures. And then it's a n choose yk. I don't know. And there it is. You're counting the number of possibilities that you can get yk successes and n minus yk failures. And what are you going to do now? Well, it's a big product. And so you can imagine I've got a product of these guys, a product of these guys, and a product of these guys. These guys don't depend on theta, so I don't really care about them. And but here I'm summing things up. Is that right? Yeah. Yeah. So it's S. Oh yeah. Yeah. Thank you. And yeah, and this C here is just, depends on y, but who cares? All right, and then you take logs again, and you take derivatives. Oh yeah, I didn't see what S is. Yeah. So exactly the thing that we're interested in over here. And we can do this, right? And there you have it. So you unscramble this and you get that. Okay, if you solve this equation for theta, and this is at theta equals theta ml, you'll get that. All right, I'll let you do that algebra. All right, so you can see that in these examples you can go through and work things out by hand, but imagine the most